Swayamprabha. Digital India. Educated India.
Okay, let us continue our discussion of spray formation, and underlying the idea of spray formation is the concept of where you have bulk liquid inside the nozzle. Bulk liquid is liquid that is still in some connected form in its entirety, that breaks up into drops slightly outside the nozzle. So, we want to see the process of the process and the forces involved that cause this bulk liquid to break down into drops. Okay. So, this we are going to investigate using a theory called linear stability analysis. Okay, before we go much further, let us understand this word stability. What does stability mean? If the simplest way to understand this is using a mechanical idea of stability, where let us say I take a ball in a trough. Let us say the trough is filled with some liquid. We all know from common observation that if I leave a ball on the side of this trough, this is going to roll down, maybe even overshoot a little bit, but eventually it will come to rest right at the bottom. Okay. So, if I take a trough of oil, then this is going to come to rest, and this is what we call the equilibrium condition. Okay. Now, if I take another trough that is also and if I drop this ball here and let us say this is all liquid, it is possible that it could come to rest here, or if I am very lucky, it could come to rest here, where it overshoots, and then you can clearly see that it has to happen by chance, or let us just say I gently placed it over there, that is quite possible. Now, these two are both equilibria. So, both of these, the previous was a case where there was only one equilibrium solution, one equilibrium condition, whereas here is a case where there is more than one equilibrium condition. In fact, if I want to be precise, there is 3 equilibrium conditions. Okay. So, what is the difference between this equilibrium condition and these two equilibrium conditions and the one where the ball is sitting on top? The fundamental difference is that if I was to take the, I will number these equilibrium conditions as 1, 2, and 3, and I am asking this question: what is different between 2 and 1? I am going to leave 3 out because 3 is the same as 1 for now. Okay. So, what is different between 2 and 1 as far as this between conditions 2 and 1? Okay. So, the difference is in the answer is in the response to small perturbations. If I took a ball at condition 1, and I will redraw the figure here just for clarity. If I displace it slightly, what the ball will do is essentially trace its way back towards the equilibrium condition 1. If I apply the same logic to this, if this is the direction of displacement, the ball is going to move away towards 3. If I displace the ball on this side, it is going to come back towards 1. So, the nature of the perturbation is going to dictate the new equilibrium solution it is going to seek. Whereas, in case of 1, whether I perturb it to its left or to its right, it is going to come back to 1. It is going to attempt to come back to 1. Now, the reason you have to understand two things here. One is an equilibrium condition, 2 is also an equilibrium condition, right. And if I perturb the system from its equilibrium position, essentially the tendency to come back to the same equilibrium position or to go to a new equilibrium position is the only distinguishing factor between 1 and 2. Therefore, in the case of 1, one is characterized by the feature two is characterized by the fact now. It is very important to understand one thing here. These are only true when you are dealing with small perturbations. Think of what I mean by small. If the perturbation, let us say if I take this sort of an angle, if that perturbation were to become large, whether it is in one direction or the other, let us say if I perturb it to where I move the ball to 2, exactly to 2, clearly it is not coming back to 1. So, what I had written in the previous slide will no longer be valid if delta theta is on the order of the angular displacement needed to take it from 1 to 2. If I go further, then it goes to 3, which is also a case where the statement is not true. Whereas, for small enough perturbations, so really speaking, in a mathematical sense, small means infinitesimally small. So, we are only looking at perturbations that are infinitesimally small in comparison to the mean state, that we want to see if I just move it to its left or to its right slightly, what will it do. Okay. So, this is if I take several equilibrium solutions of, let us say in this case the equilibrium is simply a force balance, where the horizontal forces and the vertical forces are all in balance, and that is they are all in balance at only 3 points in that trough, and 2 of those 3 points are alike in their stability characteristics, which in this case are 1 and 3, and the point 2 is different in its stability characteristics. So, mind you, they are all equilibrium solutions. It is just that 1 is stable, 3 is stable, 2 is unstable. So, what we are going to conclude from this, 1 and 3 2 is an unstable equilibrium condition. Okay. So, now what does this mean for fluid mechanics and what does it mean for sprays and atomization? If I take a condition again where, let us say I will take a trough I will take a simple case where I will place oil above water. Okay. So, just I have a beaker of oil sitting above water in a general in a gravitational field, just like that. What do we learn from this? Oil is lighter than water. So, it pretty much this is an equilibrium condition. Now, if I ask the question, if I gently place water above oil, okay, and I ask you the question, is this an equilibrium condition? The answer is yes. So, both of these are equilibria, even though density of water is greater than the density of oil. Both of these are equilibrium conditions. How do I know that? You can, in fact, the simplest way is you can actually experimentally do this. You can take a little bit of oil in the bottom of a beaker and very slowly pour water on top, not really pour, it is almost like you are placing water on top, and you can place a nice thick layer of water on top of oil. This you will be able to see it. But if I was to take this beaker of oil and water and give it a slight impulse, just give it a slight jerk, the oil, and when the oil is on water, the oil and the water meniscus both sort of undergo some oscillations, but essentially come to rest in the same configuration. Whereas, when you take water on top of oil and you give it a slight jerk, over time the water would come down and the oil would go up. You can see this experimentally. Those of you that have never done this, it is a very simple experiment to do. Go into your kitchens today and do this experiment. Try to recreate this unstable equilibrium condition and this stable equilibrium condition, and see for yourself that that is indeed an equilibrium condition unless the meniscus is perturbed. So, what is this little like shake or a jerk doing to the beaker? Essentially what I am doing is I am taking this meniscus and perturbing it just like that. Now, the top meniscus is also perturbed, but that is less important in comparison to the water oil meniscus. So, as soon as this is perturbed, the fact that right around here I have an opportunity for the heavier fluid, to come down and the lighter fluid to go up, is going to set up a motion in this direction that is going to cause it to become go to this stable condition of oil on top of water. So, every one of these little perturbations is going to set up a roll like that. Now, I did not draw these intermediate rolls here, but essentially there is also a roll there, So, as soon as I perturb the meniscus slightly, I will create these rolls. What I mean by a roll is a condition where the heavier fluid wants to come back down to the bottom of the trough and the lighter fluid wants to rise up, because that is the more favored equilibrium condition. Okay. So, the question of whether a fluid mechanics system is stable or unstable is determined by whether a perturbation of, let us say in this case, the meniscus is going to die out and cause the meniscus to return back to its original shape and condition, or like in this condition will the meniscus grow. So, think of what would actually happen if you had the meniscus growing. So, if I impose a small perturbation on this meniscus, over time, because the oil wants to rise up naturally and the water wants to come down, the meniscus shape is now going to become altered. And go to that condition. So, imagine I took this nice and flat meniscus with the water on top, oil on the bottom. and I put, let us say, in the simplest sense, a sinusoidal perturbation. A sinusoidal perturbation of this meniscus of some wavelength. So, let us say now I can also make this some wavelength lambda, and that wavelength lambda remaining the same, the amplitude of the perturbation will grow in the infinitesimally small time. As soon as I have let go of this meniscus from this perturbed shape, because water wants to come down and oil wants to go up, in the immediate time following t. So, t slightly greater than 0, what is the behavior going to look like? The shape of the meniscus is not going to be altered drastically. In other words, the functional form, let us say in this case being sinusoidal, except the amplitude will grow slightly. So, just by looking at whether the amplitude would grow or decay in a short interval of time following the perturbation itself, we are able to characterize whether the perturbation is stable, whether the system is stable to small perturbations or unstable to small perturbations. So, this is a case where the system is unstable to small perturbations. How do I know that? Because the interface amplitude is going to grow with time. Now, this kind of an instability is not something that is new. It was discovered back in the mid 1800s and it goes by the name Rayleigh-Taylor instability. Now, can you, I mean, we are only going to talk about this in a physical sense for now, but we will come to the mathematics shortly. The rate of growth going from the red line to the green line that you see here, the rate of growth is going to depend on lambda itself. Keeping everything else the same, if lambda was short or long, would cause the rate of growth to be different. Okay. And that is the one characteristic that makes the discussion of stability of fluid mechanics systems different from the stability of the mechanical system example that we discussed earlier. There the only perturbation possible is in the angular coordinate theta that we discussed. So, a slight delta theta and the force as a function of delta theta is attempting to bring it back towards theta equal to 0, the one equilibrium condition that we are after, right. So, whereas in the case of the Rayleigh-Taylor instability of superposed fluids, I can impose an infinite different types of perturbations of different lambda, of different wavelengths, and if each wavelength has certain kind of growth characteristics, then what sort of a perturbation should I really be looking at? Okay, so let me go back, rephrase what I said in a more physical way. In the previous example, only one delta theta is possible, whereas here if I want to perturb this meniscus as a sinusoidal function, there are an infinite number of sinusoidal functional perturbations possible of that flat, initially flat meniscus. But each perturbation has a different growth rate associated with it. The rate of growth of the meniscus is different for different lambda. Okay. So, what is it that so in other words, I could also have a certain lambda. Let us say for example, if I put a very small lambda perturbation on it, you will see from the mathematics later on that in fact it will be stable to that perturbation. Okay. Just because it is stable to one perturbation does not mean it is stable to all perturbations. So, in other words, we have to sort of qualify our discussion of stability from the earlier example and say that for a fluid mechanics system to be called a stable equilibrium system, that system would have to be stable under all kinds of perturbations. Okay. So, whatever be lambda, if the meniscus were to return back to this condition with water on top and oil on top, then you can say that this is a stable equilibrium condition. So, with oil on top and with water at the bottom, it does not matter how you perturb the meniscus, as long as the perturbation is small in comparison to, let us say, the thickness of water and oil. As long as the amplitude of perturbation is